In the previous two modules, we had begun with factor analysis techniques. In the previous module, actually, we had been looking at methods of estimating the parameters in a factor model. We had discussed in detail the principal component method and the principal factor method. In today's lecture, we will be looking at the maximum likelihood method of estimation. However, before we go into that, we will be looking at one very peculiar problem associated with factor models, which is referred to as the identifiability problem. And this identifiability problem plays a crucial role in estimating the parameters when we look at the maximum likelihood method. Let us go back and look at the factor model. We had x is equal to mu plus L into f plus epsilon, where x was the m by 1 dimensional observation vector. These are the original variables that we have. Mu is the mean of the process, again a m by 1 dimensional vector. L is the m by p dimensional loading vector, a matrix in this case, and f is p by 1 dimensional vector of factors. These are the common factors. Whereas epsilons are the specific factors which can be taken to be the error of the model as well. And also remember that the expected value of x is mu and the dispersion of x is sigma, which is L prime plus psi. Now suppose we make a transformation from L to L star. Let L star be equal to L into some t, where t is an orthogonal matrix. So t prime or t prime t is equal to identity. And if we do this, then we see that we can write the model again in terms of x is equal to mu plus L star into f star plus epsilon, where of course f would be a transformation from. Now if we use this t in the original model, then we can write x is equal to mu plus L t prime f plus epsilon, and then you call L t as L star and t prime f as f star, and you have a new model x is equal to mu plus L star f star plus epsilon. Now if you do that, you see that you are back with the same model. Mind you, nothing on the right hand side is known to us, and hence we would not be able to identify the difference. Similarly, if you look at sigma now becomes LT t prime L plus psi, which is basically equal to L star prime plus psi. So again the sigma looks similar. So when we are estimating the parameters from the given x, what exactly are we estimating? Are we estimating L or are we estimating L star? This is referred to the identifiability problem. And as you always know that when you have an identifiability problem, there would be restrictions required to make the estimates meaningful. So when we do the principal component method, we will be looking at this restrictions and see how we can actually get the estimates using these restrictions. Of course, we will come back to factor rotations and see how we choose the best model, in the sense that which rotation gives us the best results. Of course, that would not be from a theoretical point of view, it will be more from a practical point of view, but more of that later. Now let us look at the maximum likelihood method. So for the maximum likelihood method, we assume that x follows the normal distribution. This is possible if both f and epsilon are jointly normal. So the likelihood function L mu sigma would be given by twice pi to the power of minus nm by 2 sigma to the power of minus n by 2, and then you have e to the power of minus half summation I equal to 1 to n xi minus mu sigma inverse xi minus mu prime. And we can break this exponent as minus half summation I equal to 1 to n xi minus x bar sigma inverse xi minus x bar plus n times x bar minus mu sigma inverse x bar minus mu. And you know this summation, this is scalars, so we can always write the trace of this, and if we take the trace of this, then we can bring the sigma in front. So we have this as trace of sigma inverse summation of I equal to 1 to n xi minus x bar prime plus n times x bar minus mu into x bar minus mu prime. And you can at once see that if we maximize this with respect to mu, then estimator for mu would be x bar. So now let's put this mu hat equal to x bar into this likelihood function, and it simplifies because the last term would be of the exponent would be going to 0, it will become 0, and hence we are left with the first term of the exponent only. Now remember that we are not going to directly estimate the elements of sigma, because the elements of sigma are primarily composed of the elements of the matrix L and the diagonal matrix psi. Sigma, mind you, is L, L prime plus psi, so we need to estimate this. But there are more parameters here than the number of observations. So we need to minimize the number of parameters in this case. Okay? And to do that, remember that we are not going to look at sigma as such. We are going to look at sigma equal to L, L prime plus psi. So the original parameters would be the elements of L and the elements of psi, the diagonal elements of psi. And since there are too many parameters here, we need to put some additional uniqueness condition. One of the very popular conditions that's very often imposed is L prime psi inverse L is equal to delta, a diagonal matrix. Now having put this, we find that we can write L mu sigma, of course in this case now we can write it as mu hat, and sigma is twice pi to the power of minus mn by 2, sigma to the power of minus n by 2, e to the power of minus half. And if you can take the trace of this, we can write this as trace of A into sigma inverse, where what is A? A is n times the sample variance covariance matrix. So we can write it in terms of the sample covariance matrix. And now what we need to do is that we need to differentiate this with respect to the parameters. But remember, we have a sigma inverse which involves the parameters. And how do you take the derivative of an inverse? An easy result is that you take derivative of sigma inverse in terms of, say, a parameter theta. Sigma inverse depends on, say, theta, and you can write this as minus of sigma inverse derivative of sigma with respect to theta and sigma inverse. So you don't really need to do the derivative for the inverse, you can do it for the original matrix itself. We'll be using this result, and if we do that, and if we take derivative with respect to psi ii, it leads us diagonal of sigma inverse is equal to diagonal of sigma inverse S sigma inverse. So that is the first set of equation that we have. Now suppose we want to do the derivative with respect to the other parameters. What are the other parameters? These are the Lij's. So what would be derivative of log L with respect to Lij? If we put this equal to 0, this reduces to the equation sigma inverse delta, which should be the diagonal elements, equal to sigma inverse S sigma inverse delta. And if you put the condition that L prime sigma psi inverse L is a diagonal matrix, together we have a set of 3 equations, and these 3 equations will help us to solve for the unknown parameters L and psi. This is how the maximum likelihood works, and the details we can always work out. You can look at the text for the details, but the principle is that you need to find the derivative with the usual method of doing the maximum likelihood. Find the derivative with respect to the parameters, equate them to 0. In this case, it's going to be a little bit more complicated than that, but this would lead to the maximum likelihood estimators. But remember that you need to superimpose the condition that L prime psi inverse L is a diagonal matrix. Now let us look at how do you estimate the communalities from this. Hi hat squares would be Li1 hat square plus Li2 hat square plus Lip hat square, and therefore the proportion of the total sample variability due to the jth factor would be L1j hat square L2j hat square plus Lmj hat square divided by S11 plus S22 plus Smm, and this would tell us that how much of the variability this component actually accounts for, and that way we can choose the number of factors. This we had seen before when we were looking at the principal component method of analysis. Of course, in this case we are not directly estimating the eigenvalues, so we are not putting this in terms of the eigenvalues, but if you do the eigenvalues, we saw that if you rank the eigenvalues, then the proportion of variability explained by the first eigenvalue, the second eigenvalue, etc., would give us an idea of how much of the variability each factor was explaining. Now a question that would always arise would be how good the fit is. So we need to test a hypothesis of the form sigma is equal to LL prime plus psi against an alternative that sigma is any other positive definite matrix. Now we saw from the usual maximum likelihood method that if we just assume sigma without any particular form of it, forget about the hypothesis that it's LL prime plus psi, then the usual estimate of sigma would be the sample dispersion matrix Sn. So we can write sigma hat is equal to Sn. Remember that when we use the maximum likelihood estimator, Sn is slightly different from what we define as S, in the sense that Sn has a divisor of n. Now once we do that, and if we put this into the likelihood, then the likelihood reduces to the form Sn to the power of minus n by 2 e to the power of minus nm by 2. A is equal to n times Sn, and if we substitute that, sigma hat and the A actually cancels off, left with e to the power of minus nm by 2. So ultimately we get to Sn to the power of minus n by 2 e to the power of minus nm by 2. Now under H naught, sigma is restricted to the form of the null hypothesis, that is, it's equal to LL prime plus psi, and if we emit the parameters L and psi, then sigma hat now is L hat prime plus psi hat, and if we put this into the likelihood function now, so the maximum value under this for the likelihood function would be given by sigma LL hat prime plus psi hat, determinant of this, to the power of minus n by 2 into e to the power of minus half n trace of LL hat plus psi hat inverse into Sn. But then exponent would have a value of, this would cancel off this Sn with LL hat plus psi hat inverse, and we would be left with an exponent which would be the same as before, that is e to the power of minus nm by 2. Ratio of these two maximum likelihoods, the ratio would come out to be Sn by sigma hat to the power of minus n by 2, and since this would be, now if you take the ratio of the maximum likelihood under H naught by the maximum likelihood globally, that is, you are looking at the likelihood ratio criteria, then the likelihood ratio criteria would lead to the result that minus twice log of it would be a chi-square. And what we can do here is that we find that minus twice log of our maximum likelihood under H naught by maximum likelihood gives us the results that it is equal to minus 2 log sigma hat determinant by Sn determinant to the power of minus n by 2, and this would be a chi-square with degrees of freedom given by half of m into m plus 1 minus m into p plus 1 minus half of p into p minus 1, which reduces to half of m minus p square minus m minus p. How do you get this degrees of freedom? Remember, for the unrestricted case, the number of parameters is, you have the sigma matrix. So, the sigma would have unique elements. How many unique elements? There would be m minus 1 plus m minus 2 minus etc. up to 1 of diagonal elements and m diagonal elements, because this is symmetric matrix. So, in total there would be m into m plus 1 by 2 unknown elements in sigma. What about under H naught? Under H naught, the number of unknown elements would be the number of elements in L, which is MP, plus the number of elements in psi, which is just the diagonal elements, which is m. So, it is m into p plus 1. But mind you, we have a restriction that L prime psi inverse L has to be a diagonal matrix, and that really means that the off diagonal elements are 0, which puts the number of restrictions there as minus half p into p minus 1. So, in totality we have, it will be the number of restrictions under globally minus the number of restrictions under the H naught, which turns out to be half m minus p square minus m minus p, and then we can do a chi-square test for this to judge whether the fit is good enough. There are some variations to this, but this is a more or less a general result. In all cases, the variations also lead to the chi-square distribution, but with different degrees of freedom. But we can stick to this result as one of the ways to check whether model that we have assumed is good enough for us. In today's module, we have discussed the factor rotation in the sense that the models are not identifiable. We discussed this problem, and then we went on to find the parameters of a factor model using the maximum likelihood method. Now, we saw that the maximum likelihood method is complicated, but it requires the identifiability condition so that we can estimate the parameters reasonably. This of course can be done much simply through softwares, but you need to know the mathematics of how you do the maximum likelihood for a factor model.